Hi, apologies for the shadow this evening. I've had to switch the light on because the light's not so great upstairs in my top room. We're going to look at the alkane homologous series. This is a new term that you've come across, homologous, but simply what it means, it basically refers to a family of compounds. That all have several things in common. We've looked at the alkane series and drawn some structures of them previously, and you may have already noticed that there is a pattern that emerges as you draw the bigger and bigger structures. So some of the things they have in common is the fact that the molecular formula of neighbouring compounds varies by CH4 each time, CH2 each time. So if you look here, so we have methane here. Methane has the chemical formula CH4. When we get to ethane, which is the second in the series, we have C2H6. So basically we've added on one more carbon and we've added on two more hydrogen, so it varies by CH2. The pattern continues down here with propane. C3, one additional carbon, H8, two additional hydrogens. And it also continues on here with butane, C4, H10. So that's the first thing in about a homologous series. The second thing is that they have the same general formula. So they have the same general formula. And we represent that using a little bit of algebra. So the general formula for alkanes is C. Now we use N to represent a number, and N could be any number. And then the number of hydrogens is represented as H2N plus 2, because it's double the number of carbons plus an additional 2, and this is a formula you're going to need to learn, and you may have to apply it. You might be given the number of carbons in an alkane, and you might be asked to work out the number of hydrogens, and this works for anything. So for example, if I gave you C100 and said, what's the general formula of a hydrocarbon, of an alkane which has 100 carbons? Well, it's 2 times 100 plus 2, so it would be H202. Okay, for example. Their physical properties vary. So you have a gradual variation in physical properties. Okay, and these are, for example, boiling points, melting points, viscosity, flammability, for example. And we're going to look at some of those in a little while as well. So that's the general information about the alkane homologous series. So when we are talking about these properties that they vary, if we then relate it back to our fractional distillation column, so what I'm going to do is I'm just going to draw a very, very basic column for you, very basic. Won't have all the different fractions on it. There you go. So by now you should be able to tell me that the column is much cooler at the top than it is at the bottom. You should be able to tell me that the oil is vaporized before it comes into the column, and that the fractions condense at different temperatures. But why do they condense at different temperatures? Now up here we have what we call our gases. And these, for example, are alkane. This fraction would contain alkanes such as methane, ethane, propane, for example, butane perhaps, C3H8. Okay, and then so these are very short chain hydrocarbons. Down here at the bottom, when we get things like our bitumen come out, and these are the bitumens used for surfacing roads, tar for roofs, etc., etc. These are much longer chain hydrocarbons. or long chain hydrocarbons. So as you saw here, the chains get bigger and bigger and bigger. As we go down the column, the length of the chains in the fractions increase. So you have short chain hydrocarbons at the top, you have the long chain hydrocarbons at the bottom. The other properties that change as well. Now these short chain hydrocarbons have low boiling points. That's why they remain in a gaseous form. That's why they remain gases all the way up the column here, and they only start to condense when you get up to the top here. And in fact, often they don't condense at all because it's only about 20 degrees up here. And these alkanes have very, very low boiling points, often below 0. So they have low boiling points. Down here, the reason why these basically come straight in as a vapour and then condenses because they have very high boiling points. Further up the column, you've got things, for example, such as the fraction which we use for petrol, and that contains octane. So if you remember, that's 8 carbons in it. So that that has a relatively low boiling point, but also it has a relative low flammability. Oh, sorry, high flammability. As do the gases up here. Down here with your long chain hydrocarbons, they have low flammability. They're not easy to set light to. Okay, so they are not easy to set light to, which is a good thing really, because you wouldn't want our roads being on fire constantly. Also, these have what we call high viscosity. And viscosity is ease of flow. So your long chain hydrocarbons flow very, very slowly. They're thick, and you know they're quite hard to flow. Your shorter chain hydrocarbons, these have low viscosity, so they flow much easier. I'm going to write flow easily. Here they're thinner, and that makes them quite useful actually. You know, for example, the petrol fractions, you need them to have low viscosity so they can go through the engine. Down here, your bitumen, you want it to have high viscosity because you don't want it flowing all about the place when you're laying a road, for example. So they're your key points about the physical properties of the alkanes. So short chain hydrocarbons found towards the top or condensed towards the top of the fractional distillation column. Low boiling points, these are your key bits, low boiling points. High flammability, they're easy to set light to. Low viscosity, they're very thin, they're runny. Your long chain hydrocarbons, which are found towards the bottom. High boiling points. Low flammability, they're not easy to set light to, and high viscosity, they're very, very thick. So remember, as you go down the column, the chains in the hydrocarbons get longer and longer. Long chain. Okay, thank you very much.